All right, class. So in the last class, we had completed till the revision of current electricity. Current electricity was over. Now we have to start the revision of magnetic effects of current. Magnetics, let's start with. So the first important law that comes is Biot-Savart's law. So Biot-Savart's law, just remember, firstly, Biot-Savart's law, this is directly proportional. Magnetic field is directly proportional to the current that is flowing across the conductor. Magnetic field is directly proportional to current element. If this is your current wire, then this a small portion is known as current element. Then if you take a point from this point and the position vector, an angle will be made. So magnetic field is directly proportional to this sine theta. Fine, this is directly proportional to sine theta. And inverse square rule is followed up here as well. That is 1 by r square. So combine everything. You will get dB directly proportional to I dl sine theta divided by r square. Here you will put a constant, that is k. K, or you can directly put mu naught by 4 pi. I dl sine theta divided by r square. This is your Biot-Savart's law. Now class, what type of questions are possible in your board exams? There can be a comparison between Biot-Savart's law and Coulomb's law. So firstly, you should remember the definition you have to mention, and then you have to compare their points of similarities or differences. Whenever a question will come, first you will tell kq square by r square is that law formula, and here k ideal sine theta by r square is the formula. And points of similarity you can mention, both follow inverse square rule, right? Both follow inverse square rule, r square, inversely proportional to r square. Both are long range fields. That is also similar. Let me do one thing. Let me write it over here. So both follow inverse square rule. Second, both are long range. Both are long range fields. And third, a superposition is applied to both of it. Superposition is applied to both of it. Fine. And then points of differences are also there. Magnetic field that is produced by a vector source in one is a current element I, and in Coulomb's law it was charge only, right? In magnetic field you had current, but here you have charge only. Then second point of difference you can analyze is that direction of electrostatic field is along the displacement vector that is joining the source and field point. Correct. Here the direction of electrostatic field is along the displacement vector joining the source and the field point. And then lastly, you can say here angle is there. In Coulomb's law, that is not dependent on angle. So these are points of similarity, some points of differences between now before Ampere's circuital law. No, just a second. Okay, before this, let us just discuss the formulas as well. So formula for formula for magnetic field at the center of circular square. Center of circular coil. So that is mu naught I by 2r. This radius is r. And then if it is at the axis, let's say at this axis it is there. Then we'll write, suppose the separation is A. Radius is again small r. So magnetic field is mu naught I A square by 2r square plus A square to the power 3 by 2. This magnetic field due to circular square, right? Circular square if it is asked to you. Apart from this square, no need to remember semi. Semi-square will be exactly half of it. Mu naught I by 4r. Then you can remember it for infinitely long straight wire. This will be mu naught I by 4 pi a. This is the basic which you have to remember. Fine, note it down. Note down just this part, not the law. Then we'll practice some question. See class, these are two loops. L1, L2 are given, radius is given 3 centimeters, others radius is 4 centimeters. Their separation from a center is taken, not center, from a point is taken as 4 centimeters for L1 and 3 centimeters for L2. You have to find the value of current in the second loop so that the net magnetic field at this point becomes 0. So this point is just like neutral point you used to find in your electrostats. The way when net force was at neutral point you wanted to calculate, so you put it as 0, you equate it as 0. So the two coaxial circular loops L1 and L2 of radii 3 centimeter and 4 centimeters are placed. What should be magnitude and direction of current in the loop L2 so that the net magnetic field at the point O is to be 0. So here see. So net current should be 0. So current for first loop. Just now we have seen this is like, actually this was drawn like this. Means this is point is lying on the axis of it. This is not linear. So this will be mu naught I1 r square. So 3 centimeters, 0.03 whole square divided by 2 into 0.03 whole square plus a square 0.04 whole square to the power 3 by 2, 3 by 2. This is equal to mu naught I. I1's value is 1 only. Let me write it as 1. So mu naught I, then this will become 0.04 whole square by 2 into 0.03 whole square plus 0.04 whole square to the power 3 by 2. See, denominators will get cancelled. Both the denominators are same. Mu naught will get cancelled. I will be 0.03 whole square divided by 0.04 whole square. This is the current I here for this loop. So 9 by 16. This will be 9 by 16. That is 0.56 amperes. Note down the question and the solution. Okay, now coming to Ampere's circuital law. So a very easy topic. Ampere's circuital law basically states that the way you had Gauss theorem, which said 1 by epsilon naught times the charge enclosed is your total electric flux that will be flowing. It says that the line integral of magnetic field means B dot dl. Integration of B dot dl. This is actually equal to mu naught times the current that is enclosed. This is mu naught times the current that is enclosed. So according to Ampere's circuital law, line integral of magnetic field along a closed loop is mu naught times the total current enclosed by the loop. So B dot dl is equal to mu naught I, but I has to be I enclosed, not just any I. You have to choose Amperian loop, then put the value of dl, means integrated. If it's a circle, put 2 pi r. If it's a square, then a square, whatever is the total length of the material, and then solve it. But choosing Amperian loop is must. Please class, these two cases which I have discussed with you in the class, remember these two. Mu naught IR by 2 pi a square, this case when you're, and the graph also for it. I think we did a graph also. Yes, this graph. Because earlier when it is inside, it is directly proportional to R. But for the outside formula, there wasn't any R. I'll show you here. See, this was the case when it was inside. B is equal to, the point was taken inside. So Amperian loop was taken inside. So mu naught IR by 2 pi A square. And when it is outside, this is mu naught I by 2 pi R. So this becomes the formula for it. Okay, now coming to solenoid. Solenoid's formula, I hope you all know formula of solenoid and toroid. For solenoid, formula is B is equal to mu naught Ni, where N is number of turns per unit length. This is for solenoid. And for toroid, it is B is equal to mu naught Ni, but here N is number of turns per unit length, and length for a solenoid is 2 pi R. This is for toroid. Let's directly practice numericals. Okay, class. So 0.5 meter long solenoid has 500 turns and has a flux density of 2.52 into 10 to the power minus 3 Tesla at its center. Find current in the solenoid. See, number of turns per unit length you have to first calculate. This is a simple question. This is actually from your previous year. That's why I just wanted to discuss it with you once. Number of turns are 500. Now per unit length is 0.5 meter. That makes it 1000 turns per meter. Please class ensure whether it is number of turns per unit length given to you in the questions or number of turns given. So now B is equal to mu naught Ni. See, B is equal to mu naught Ni. So I will be B divided by mu naught N. Magnetic field is 2.52 into 10 to the power minus 3. Mu naught is 4 pi into 10 to the power minus 7. N is 1000. So when you'll solve this, see, 1000, 10 to the power minus 6, 10 left, 425, 100. Then again this pi, it will be around 2 amperes. It should come around 2 amperes. Just check. 1.99, it should come. Just check and let me know. Note it down. One more numerical I'll write. See, this says that nobody got any answer. It says that a copper wire having a resistance of 0.01 ohm per meter is used to wind a 400 turn solenoid of radius 1 centimeter and length 20 centimeters. Then find the EMF of a battery, which when connected across the solenoid would produce a magnetic field of 10 to the power minus 2 near the center of solenoid. So first let us find out the magnetic field. C class, length will be, class length can be written as 2 pi r into the number of turns. So 2 pi r. So 2 pi into number of turns will be, this is 10 to the power minus 2 into 400 meter. And you have resistance per unit. Resistance per unit length, how much? 0.01 meters. Okay. So total resistance will be what? Multiply this. Total resistance will be 2 pi into 10 to the power minus 2 into 400 into 0.01. So this is 8 pi into 10 to the power minus 2 ohms. Now number of turns per unit length, when you will calculate, when you will write down the number of turns per unit length. This will be 4,000, 2,000 per meter. Now you have number of turns. So from B is equal to mu naught Ni. I can be written as EMF divided by resistance. Put it here. So B will be mu naught Ne by R. From here, you can easily calculate EMF. That will be BR by mu naught, and rest of the things you have it with you. Put in the value, you should get your answer as 1 volt. Check C. Quickly note it down, then we'll start with Lorentz force. the magnetic force on moving charges, Lorentz force was QVB sine theta. Lorentz force was QVB sine theta. And you have Fleming left. Yes, so F is QVB sine theta. This is your Lorentz force, magnetic force, basically. This is your magnetic force. So total magnetic Lorentz force is combined force, that is electric force plus magnetic force, which has QE plus QV cross B. So you'll take QE plus V cross B. This is the net force. Now, apart from this force on a current carrying conductor, this is written as I L cross B, which is written as ILB sine theta. Let us practice a question on this. It says that a straight wire of mass 200 gram and length 1.5 meters carries a current of 2 amperes. It is suspended in midair by a uniform horizontal magnetic field. What is the magnitude of magnetic field? So here, if a straight wire is kept, it is suspended in midair. If a wire is kept, it will be having gravitational force downwards, right? And upwards will be the force that is applied. So force will be ILB sine theta. that is ILB only. Basically, you have ILB and the gravitational forces, mg. Equate both these forces. So that makes it mg is equal to ILB. So from here, magnetic field will be mg by IL. So mass is 200 into 10 to the power minus 3 kg. Acceleration due to gravity is 9.8. Current is 2 amperes. Length is 1.5 meters. I noted down. Okay, now torque on current carrying coil. So this is a rectangular coil on which forces are exerted. So this derivation can also be asked to you. Torque's derivation can also be asked to you. M cross B. as well as you have NAIB as well. M is magnetic moment, NAIB can also be used, NAIB sine theta. So net force on current carrying coil in uniform magnetic field is 0, and it is independent of shape and size of the coil. Now let us practice some questions on torque. The question says a rectangular coil of 100 turns has length 5 centimeters and width 4 centimeters. It is placed with its plane parallel to a uniform magnetic field, and a current of 2 amperes is passed through the coil. If the torque acting on the coil is 0.2 Newton meter, find the magnitude of magnetic field. This is a very easy question, class. Try it by yourself first. See, by now you all should have sent your answers. Khalid, Salman, Memuna, Sara, all of you should be able to solve this. Send me your answers. Calculation part is not difficult for this question. 2 minutes, then I'll discuss it. Yes, only Khalid has answered correctly. See, torque's formula is what? Torque is NAIB sine theta, class. Okay, Sarah is also correct. Good, Sarah. So magnetic field we have to find out. Magnetic field will be torque divided by NAIB, because sine 90 is 1.5. Good, Salman. Correct. So torque is 0.2, number of turns 100, area 2 into, this was a rectangular coil, no? So area we have to find out. So 2 into 0.05, because 5 centimeters, 2 into L into B, 4. Then current is 2 amperes, and magnetic field. Okay, magnetic field we have to find out. Magnetic field we have to find out. So once you'll solve this, you will get 0.5 Tesla. Correct, class. One more question, let's practice. Then we'll complete moving coil galvanometer and move to the next chapter of magnetics. This is also simple question, class. Please try to answer this. Memona, you also. Khalid, you can round off such answers also. You're correct, like 0.1256, so you can write it as 1.3 as well. Sarah, 0.1256. Correct, correct. So see, torque will be again NAIB sine theta only. But area will be this time pi r square. That will be the difference. And theta is not 90, 30 degree. So torque will be 500 into 1 into magnetic field is 0.4. 0.4 into then pi r square will be 0.02 whole square into sine 30 degree. So this will be 0.1256, which you can approximate and write 0.13 Newton meter. Quickly note it down. Last topic we have to discuss, and we have to move on to the last segment of magnetics. Now, moving coil galvanometer, it's a device that is used to detect current. Principle is that a current carrying coil is placed in a magnetic field. It experiences a current dependent torque which tends to rotate it, right? Now, in the construction of it, there are two magnets in between. Soft iron core is there, spring is present, and a pointer is there. This pointer moves on a scale, both the magnets are there. So now, because of the radially directed magnetic field, the spring allows the pointer to move, and that helps to detect the current. So torque, deflecting torque is equal to the restoring torque. And when this is the case, your restoring torque is equal to the deflecting torque. You get the deflection as NAIV, the torque formula, divided by the constant. This is known as torsion constant, which is just a constant, you can say. Now, two types of sensitivities are there. Current sensitivity and voltage sensitivity. Current sensitivity means current deflection per unit current, and voltage sensitivity means deflection per unit potential difference or deflection per unit voltage. Now, if you put in the value of theta as NAIV by K, and in both the cases, you will get currents value as NAB by K, and voltage sensitivity you will get voltage sensitivity as NAB by KR. Fine, this is it. So deflection per unit potential difference. Now, to convert the galvanometer into ammeter, you have to connect a low resistance parallel resistor along the galvanometer. This is known as shunt. So the formula, because they are connected in parallel, so you have to equate with the potential difference. Here you will get the value of shunt as Ig into capital G divided by I minus Ig. Fine. Now conversion of galvanometer into voltmeter. Now here you have to connect a high series resistance in high resistance resistor in series along with the galvanometer, where you will get the final answer of the resistance across this high valued resistor as V divided by Ig minus capital G. Here V is the voltage, Ig is the current across the galvanometer, and G, capital G, is the resistance across the galvanometer. All right, so this was what you had in your magnetic effects of electric current, moving charges and magnetism. Now from your magnetism and matter, that also has some portion. Now mainly you have the concept of bar magnet. Totally you have to do bar magnet in detail. So there are certain properties of bar magnet, that it has attractive property, means it attracts, north pole attracts south pole, and directive property means if you suspend a freely bar magnet in the magnetic field, it will align itself automatically along the north-south direction. And if you cut the magnets, both the polarities will develop. That will indicate that monopoles do not exist. And magnetic induction means that it will be able to induce magnetism. Like iron ball is kept, then you will notice that after rubbing a magnet with iron ball, you will notice that iron ball is having certain magnetic properties. Now terms related to magnetics. First is magnetic pole. Then you have magnetic axis. Magnetic poles means north and south pole. Right, two poles are there. So north pole and south pole. Magnetic axis means a line like you are cutting it through a longitudinal axis or transverse axis rather. So magnetic axis means you are cutting the magnet into two halves from the north to the south pole. This is magnetic axis. So line passing through north and south pole. And magnetic equator is the perpendicular line to the magnetic axis. Length means the entire length of the magnet means complete separation between north and south pole. Now this will be again a revision of what we have already done in electrostatics to what you have to study now. So in electrostatics, you have electric charge whose SI unit is coulomb. So positive and negative charge is present. Both can have same magnitude, both can have opposite magnitude, both can have opposite signs as well. And then here magnetic charge basically means magnetic pole strength, means how much is the value of north pole. That is what is meant by magnetic charge. So again, you have north and south poles. This indicates the polarity only. Then you have the concept of dipole. Dipole basically means two opposite charges are there having same magnitude but opposite signs. So if opposite signs are there, they are having same magnitude and separated by a small separation. So dipole will be the separation between the charges into the charge. The SI unit is coulomb meter. Same thing for magnetic dipole also. You have the separation between both the magnetic charges, north and south pole. Both should have the same magnitude and they should be separated by a distance. And this formula is used a lot. You have also seen the derivations also, small m into L. That is magnetic strength into the separation between them. SI unit is ampere meter squared. Then we get the values of electric fields or magnetic field for two cases. Either for axial line of dipole, then magnetic field for axial line. Then you have for axial line, you get the formula as 2 kp by r cube. Now P is dipole moment in electric field. For magnetic field, dipole moment becomes magnetic moment M. So 2 kp by r cube, here 2 km by r cube. Now, one more thing, that the constant in electrostatics is 1 over 4 pi epsilon naught, but the constant in magnetic field is mu naught by 4 pi. So this is also a difference regarding the constant terms. Constant term also makes a difference in it. And equatorial line has minus Kp by R cube. So in equatorial line, you have the formula of magnetic field as minus Kp by R cube. Equatorial line means the point is located perpendicular to the line that you have joined to the axis. All right, that is the line that you have joined. So that is known as equatorial point. So axial point means along the axis. If you keep on extending the axis of the dipole, that will lead to you towards axial line. Then equatorial means minus Kp by R cube. Torque is there. Torque is P cross E in electrostatics, PE sine theta, and M cross B, MB sine theta in magnetics. For work done, you have minus PE cos theta 2 minus cos theta 1, which is initial angle where the dipole was aligned with the electric field, and the final angle. Now, what is the work done of rotating torque? Torque will try to align the magnetic field in the torque will try to align dipole along the electric field. Same work magnetic dipole moment will do to align the bar magnet along the magnetic field from theta 1 to theta 2. Theta 1, theta 2 are some different theta 1 and theta 2 are some different angles that are present from where the torques were aligned. Now, after work done, you have energy also, potential energy. So minus PE cos theta 2 minus cos theta 1, this remains the same because all the work done is converted into potential energy. This we have seen. And same way, work done is converted into potential energy in the second case. That is your magnetostatics. So these are the differences and commonalities between it. This we have discussed, all these things. Okay, some terms related to magnetism. Some terms that are related to magnetism is the magnetizing field. Magnetizing field is basically a field that exists in vacuum and induces magnetism. So magnetic field is B is equal to mu naught Ni. Like for a solenoid, you had the magnetic field as B is equal to mu naught Ni. So if it exists in vacuum, you can simply say it is magnetizing field. Then you have magnetic induction also, number of magnetic field lines that are present. Number of magnetic field lines that are present. Then magnetizing field intensity is there. Magnetizing field intensity is represented by H, which is number of turns times the current. N into I, number of turns times the current. Then intensity of magnetizing, you have magnetic moment per unit volume. Like current density, we had no current per unit area. So similarly, it's like intensity of magnetization. Just the problem that will arise, all the terms are very similar to each other. If you will look, intensity of magnetization, magnetizing intensity, all the terms are very closely located with each other. So that's why just have a clarity of what you are studying, which term you are understanding, because then it will create a lot of confusion. All right, class. Then magnetic permeability, we have studied. Permeability is the same permeability which you see in 4 pi into 10 to the power minus 7. Same permeability values that governs different media for the calculations of magnetic field. How the magnetic fields change with different media with respect to the magnetic poles. So this constant is 4 pi into 10 to the power minus 7. If you have vacuum air or other material, this value becomes different. So we multiply it with mu r to get the mu for any medium, which is known as relative permeability also. That is the next point. Relative permeability is the ratio of the permeability of medium to the permeability of free space. Free space, whenever we say, that is air or vacuum. Then magnetic susceptibility was intensity of magnetization divided by magnetic field intensity. This was the difference that arised in here. And there was an important relation. This relation separately comes as a 2-marker to write the relation between mu naught and xi. Now, classification of magnetic materials. Class, I have told you in the class also that this classification between the materials is very important, because without this classification between the materials, you'll not be able to solve most of the questions. Most of the questions have this involved. This table is there also that I had shared you on WhatsApp also, where all the comparisons between paramagnetic, diamagnetic, all these substances were also made. So that table is very important. I hope you all have gone through that, because that is not deleted from your syllabus. And if it's not deleted, chances are there you can be asked to write about it. Fine. So if I discuss the differences between diamagnetic, paramagnetic, and ferromagnetic substances, see, first point is effect of magnets. So in diamagnetic substances, they are feebly repelled by magnets, means they are weakly repelled by magnets. In paramagnetic substances, they are weakly attracted. So weakly repelled, weakly attracted. And for ferromagnetic substances, they are strongly attracted. So feebly attracted, feebly repelled, and strongly attracted. So this was the first point, effect of magnets. Second point, in external magnetic field, for diamagnetic substances, they acquire very weak magnetization, and that too, it is located in opposite direction of magnetic field. This weak magnetization, this is located in opposite direction. In paramagnetic, it is located in same direction, and in ferromagnetic, these are not weak. Strong magnetizations are there. Then in presence of non-uniform magnetic field, they tend to move slowly from the stronger to weaker parts of the field, diamagnetic. And paramagnetic tend to move slowly from weaker to stronger parts of the field. Here, and paramagnetic then move quickly, very quickly. Para and dia move slowly, but ferro moves very quickly from stronger to weaker parts. Then in uniform magnetic field, this was non-uniform, slower to weaker one. If you have a uniform magnetic field, then a freely you can say freely suspended diamagnetic bar magnet that will align itself perpendicular to the field. And if you take as the same thing for paramagnetic, that will align itself parallel to the field. And for ferromagnetic also parallel. Ferro para parallel, dia perpendicular. Uniform magnetic field. So what all we have discussed? Effects of magnets: dia weakly repelled, para weakly attracted, ferro strongly attracted. External magnetic field: weaker magnetization in opposite direction for dia, para weaker magnetization in the direction of magnetizing field, and para same direction, strong magnetization field. Non-uniform magnetic field: in dia, the magnetic field moves from slowly to stronger, slowly from stronger to weaker parts. In para, it moves slowly from weaker to stronger, and in para, it moves weaker to stronger, but quickly. And in a uniform magnetic field, freely suspended magnet, when it is there, it is perpendicular to field. Freely suspended magnet aligns itself parallel in paramagnetic, and it aligns parallel, same thing in ferromagnetic. These are very important points. Some examples you can remember, like for some examples, I must have written here only bismuth and all. Bismuth, copper. So copper, lead, silver, gold, sodium chloride, these are all the examples of diamagnetic substances, because all the three states of matter can exist there. Then for paramagnetic substances, aluminium, sodium, copper chloride will come here, and some of the STP states, all the three are valid here also. And for the final one, ferromagnetic, you have nickel, iron, cobalt, gallium, all these alloys basically. You must have heard of that alnico, aluminium, nickel, cobalt together. So that is also there, alnico. That can also be categorized under ferromagnetic. Lastly, you had earth magnetism. So in earth magnetism, yes, Memuna, the class will end within 5 minutes also. So if you want, you can leave or you can stay, because this is the last topic and a very small topic. You can leave though, Memuna. The earth magnetism, firstly, you have laws of magnetism, where flux is fine, total charge enclosed by epsilon naught. So here in magnetic field, these were the 4 laws. No, we'll start with earth magnetism. So some lines, some just understand these topics. Rest of the things of earth magnetism is very easy. You have a geographic equator and a magnetic equator. Geographic equator is the actual equator, south to north pole. And then you have a magnetic equator, that is the equator of the magnet if Earth acts as a magnet. So magnetic axis will be present, length of magnet will be present, magnetic equator will also be present. And this is the pole of this is actually a line passing through the north and south pole, which you call as the geographical axis or axis of rotation. So magnetic axis, magnetic equator, the geographical and magnetic equator, geographical axis, and the magnetic equator. So see, if you keep a freely suspended magnet, then one of the components of magnetic field, if you align with the magnetic meridian, that will be forming an angle delta. So one component, a horizontal component, will be B cos delta, and the perpendicular component will be B sin delta, right? B cos delta and B sin delta. So when you take the ratios, angle of dip becomes BB divided by BH, means magnetic field vertical divided by magnetic field horizontal. Fine. So that was all about your magnetics unit. Any doubts from this class? From any units, any question you had having difficulties? Because on Wednesday we'll complete EMI, AC and EM waves. First book revision will be over. So what all doubts you are having, if you're practicing, keep on sending me the doubts on WhatsApp at least. Clear by all of you? Yes, no, slept. So only
Yes, teacher, clear.
okay, fine. Fine class, then you all can leave. Wednesday we'll continue EMI,